In this video, we're going to see the reasons and also examples for non-hydrostatic pore pressure. Um, we have said before that we can calculate sometimes pore pressure with a hydrostatic gradient. This is valid whenever we have a free body of water without any rock, like for example, from the sea level to the seafloor in case we're offshore. And also whenever we are into the porous medium and we have a connected system of pores which is in hydrostatic equilibrium with the surface. So this is equivalent to saying that we may have a capillary tube that goes at a given depth, let's say for example here at 4,000 feet, to the surface connected to a tube and is in equilibrium with the free level of the water in the sea. However, sometimes this is not the case, and the key aspect in order to capture this is that there is no connection with this free surface. And whenever that happens, we might have cases in which the pore pressure does not follow a hydrostatic gradient, but follows some other type of gradient, which is non-hydrostatic, and we need to take into account into geomechanics in order to accurately capture effective stress. All right, so here we have one example of field data in which we have the vertical stress with this dashed line, and we have also data for pore pressure. The circles are real data, and in the dashed line with blue, we see the hydrostatic trend. We're going to see in this video the reasons for this overpressure, which is we say that we have overpressure whenever the pore pressure is higher than the hydrostatic pore pressure. And also we're going to see how to calculate that. But remember, in many real cases, the pore pressure is not going to be hydrostatic. This is something that we have to figure out first before we do any geomechanical analysis. All right, in order to get started, we're going to define a variable which is called the overpressure parameter lambda p, and it is defined as the ratio between the pore pressure at the given depth and the total vertical stress at the given depth. When this overpressure parameter gets close to 1, like for example around this region, that means that you are very close to the total vertical stress. When this overpressure parameter approaches 0.44 in onshore conditions, that means that you are close to the hydrostatic pore pressure. In offshore conditions, this is going to change. Hydrostatic doesn't mean 0.44 because you need to take into account the thickness of the water or the depth of the seafloor. But what is going to be always valid is that whenever lambda p approaches 1, that means that you're close to the vertical stress. And this overpressure parameter cannot be higher than 1. Why? Because if it is higher than 1, that means the pore pressure is higher than the vertical stress. And as we're going to see later on, this is not possible over long times, especially over geological times, because that means that you would have a hydraulic fracture in this place. And if we do have a hydraulic fracture, at some point that pore pressure is going to dissipate and is going to equilibrate with the total vertical stress. So this pore pressure cannot be higher than the vertical stress. Whenever we get close to the total vertical stress, that means that this is an overpressure area. All right, so let's see what are the reasons for having overpressure in a given formation. The first reason that we're seeing here is what is called a mechanism called by a difference in density in a given formation of the fluid. And this happens mostly in reservoirs, and it can get quite big, especially in gas reservoirs. So that's why we have this example. Example that we have a nice anticline, which constitutes a structural trap. This is a formation which is all filled with water except under the anticline, which is filled with gas. If we draw and we trace a profile of pressure through the center of the anticline in this line BB, in this cross-section BB, we're going to find out that the gradient of pore pressure in this section BB is going to have a jump compared what you would have where you don't have the gas. For example, in a section AA. Let's assume that the section AA is in equilibrium with the surface and is under hydrostatic pore pressure. Then that pore pressure will follow in section AA the hydrostatic trend. However, when you get into the gas region, if this gas is connected within the gas, the gradient of pressure is not going to be the gradient of the density of water because there is no water here. We have a connected gas region. Therefore, within the gas, the gradient of pore pressure is going to be the gradient of gas. And we know that gas is a lot lighter than water. Therefore, the pore pressure or the gradient within the gas region is going to be smaller than the gradient within the water region. Why? Because the density of gas is smaller than the density of water. The result of this is that at the gas-water contact line, the pressure has to be the same in order to be in equilibrium, but far away from that gas-water contact line, like for example at this region, close to the cap rock, there's going to be quite a large difference between the gas pressure in green and the water pressure. And this is going to cause overpressure in this formation. For example, if you were drilling a well through the center of the anticline and you're using a given drilling mud weight, which is good for coping with the hydrostatic pore pressure, well, you might be more or less fine as you go deeper and deeper, but once you jump into the gas field, and especially if you didn't know that there was a gas reservoir over here, suddenly you're going to face a pore pressure, which is much higher than the one that you had before. And that might produce, for example, a kick in drilling. All right, so this is the first reason for overpressure, and it's a hydrocarbon column, and it's due to the difference in mass density between fluids within the rocks. The second reason is changes in temperature. We know that changes in temperature make most of fluids and solids dilate. So for example, if suddenly you have an increase in temperature and fluids cannot dilate because they are hydraulically unconnected from the surface, you may see a rise in the pore pressure because the fluid is trying to dilate and it cannot. The third type is due to chemistry and the evolution of rocks. There are some clays, like for example, montmorillonite, that when it gets deeper and deeper, it goes through a diagenesis that results in some of the bound water to, here we go. Here it results some of the water to going into another type of binding with the molecular structure of the clay that takes less space, and some free water gets released. So this free water that gets released, and if it has nowhere to go, also is going to cause an increase in pore pressure. A fourth example is hydrocarbon generation. When organic matter transforms into hydrocarbons, also there are reactions in which some of these molecules are going to combine, are going to change volume, and the result of that is going to be that, again, if you are under closed conditions and the new fluids have nowhere to go, this is going to result in an increase of pore pressure. I have one example related to hydrocarbon generation, and it is over here. It's particularly valid for unconventionals. In unconventionals, we know that in many regions we do see overpressure, that is pore pressure higher than the hydrostatic pore pressure. And one of the reasons why we have this overpressure, we'll see that there is another one, is the generation of hydrocarbon fluids. So for example, here in this plot, we see in the y-axis depth and several tracks. In the first one, we see the composition of this particular source rock, and we see that as we go deeper and deeper, there is more kerogen, more oil saturation, and also at this location, there is higher pore pressure. Again, this is partially related to the generation of hydrocarbons in source rocks. This is actually good for unconventionals because higher pore pressure allows us to recover oil and gas more easily from these formations because there is more pressure drive. All right, okay, these are 4 reasons that we have seen for overpressure, and now we'll jump into another reason, which is one of the major reasons for excess pore pressure in sedimentary basins. And this is what is called disequilibrium compaction. And as the word says, it means that there is a process of compaction that has not been equilibrated with time. Okay, let's see what are the reasons for this. There are many places, especially sedimentary basins, in which we have sequences of rocks that get deposited with time. In this example, what we are looking at is the sequence of the structural column of along 6 wells in the Gulf of Mexico, where we see sequences of sand in yellow and shale in gray. And we can see in this example that we have several layers of sand which are interbedded with shale. And this happens over millions of years, right? Well, if you have some of these sands and shales to deposit so quickly such that the fluids, remember this is all saturated with water, if the water cannot escape when the next layer, for example, this shale here is deposited, if there is no time for that water to escape, then that's going to generate overpressure. Why? Because you are depositing these layers with time so quickly that the water underneath cannot escape, and this mass of sediment cannot compact and reach equilibrium. You may think that this is somehow difficult to imagine because over geological time, over thousands of years, you would expect the water or the sediment to compact and the water to escape. Well, some of these formations, especially shales, they have such a low permeability that even over thousands of years, the pore pressure may not get released as you have a process of compaction. And this is what is called disequilibrium compaction. Basically, when you add a weight and you compact a porous medium, the compaction and how much it takes for this pore fluid to get out and for the pressure to get released and come back to hydrostatic is going to depend on properties of the fluids, like for example the viscosity of the fluid, but also properties of the porous medium. What is the compressibility of the medium, and also what is the permeability of the medium. Here we have a more realistic example of a porous medium in which originally we have a hydrostatic pore pressure. What we're going to do is we're going to add a weight on it and see how the pore pressure is going to vary. Before I show the solution for this, just keep in mind that if you have a rock or a porous medium in general for which you apply a load, and if you have no drainage in the bottom, if you apply very quickly, you're going to be loading not only the rock, the mineral part, but also the pore fluid itself. And what that's going to cause is an increase in pore pressure. All right, let's see the solution and then we'll talk about this equation. The solution right after loading is the state is going to move from hydrostatic, like this one, quickly to also hydrostatic, but with a higher pore pressure everywhere in this mass. And with time, fluid is going to start to escape from the top layer, because this is the one that is draining. The bottom one in this example is not draining. And when this fluid starts to drain, the pore pressure, it will go back to the previous value as a function of time. The top surface is going to drain first, and as we go deeper and deeper, this porous medium is going to drain later and later, which that means that's going to create a variation of pore pressure, which is going to depend on time and also on the properties of the fluid. How much time it takes for this system to go to the overpressure condition everywhere to the original condition, again, it will depend on the properties of the medium, like permeability and the compressibility of the medium, but also on the fluid properties. It's not the same releasing in the medium a fluid like a gas, which has a low viscosity, than a fluid like water, which is going to have a higher viscosity. And the equation that explains this is called the here the diffusivity equation for pore pressure, and it tells you the variation of pore pressure in time with location. And the characteristic parameter that links these two quantities and tells us how fast the pore pressure is going to dissipate is this diffusivity parameter that, as we were saying before, depends on the compressibility of the medium, in this case in terms of stiffness, M, the permeability of the medium, and the viscosity of the fluid. The higher the diffusivity parameter, the lower is going to be the time for pore pressure to dissipate. The smaller the diffusivity parameter, then the higher or the longer it's going to take to pore pressure to dissipate. And let's see here one example. We can work with this diffusivity equation and calculate what is called the characteristic time for pore pressure diffusion. This is approximately how long it would take for such a system to have pore pressure dissipated. And this is proportional to the square of the drainage length, which in this case is from here to the top, and it means what is the distance I would take for, or the maximum distance I would take for any molecular fluid to drain, and in this case it would be from here to the top, that's the maximum distance, divided the diffusivity parameter. And if you work on example 2.5, here we're presenting the case of two layers, one made out of sand and another one made out of clay or shale, 100-meter thick. And the question is how long it would take for this 100-meter thick sediment to have pore pressure dissipated back to more or less the normal or the original value, where the properties of the sand are permeability of 100 millidarcy and a compressibility, or in this case a stiffness of 1 gigapascal, and in this case a mud rock, with a permeability of 100 nanodarcies and about the same compressibility. The important parameter really here is the permeability. And we put these two values into the equation 2.17. You can calculate that for a sand, it would take about 1 day for the pore pressure to dissipate. And that kind of makes sense. That's what we would expect for this reservoir to dissipate the pore pressure if there is a pulse of pore pressure. However, for the mud rock, it's going to take 3,000 years. This is quite a long time. And what this is trying to tell you is that these mud rocks with very low permeability are going to take a very, very long time for pore pressure to dissipate. And these mud rocks are the ones that are going to act as vertical seals in this sequence that is going to lock off some of the pore pressure in lower formations and result in this disequilibrium compaction and overpressure in the formation. The result of this equilibrium compaction is also that the porosity in some of these formations underneath a regional seal is going to be lower, it's going to be higher than expected because they haven't compacted as much as they should for their depth. And this property, a porosity higher than expected, is going to be what is going to help us to calculate that overpressure. Okay, let me share with you one example here about typical depths for overpressure in the North Sea or also in the Gulf of Mexico. We can see that generally overpressure starts at more or less 2,000 meters to 3,000 meters from the seafloor. Generally, until that depth, we have hydrostatic pore pressure, but as you go deeper and deeper, you start to see higher pore pressure, and this is a challenge for drilling. We're going to see that later on, but usually this is the trend. The deeper you go in offshore conditions, the higher the pore pressure is going to be. The more the departure from hydrostatic pore pressure is going to be. And this depends from place to place. And actually today, right before this recording this lecture, I attended a meeting in which, let me share with you the original title of this paper, in which there is a map of pore pressure gradient for the Gulf of Mexico, which allows us to see a little bit more in detail. Let's just concentrate on this one about overpressure depending on location. So depending on depth, usually these are deeper locations too, we have different gradients of pore pressure, and this depends again on depth and also on location, and this is the case for the Gulf of Mexico. Remember, overpressure is a very important variable that we're going to have to take into account in geomechanics, either for offshore conditions, for drilling, or also for onshore conditions, especially for unconventionals. All right, so let's come back here to the main document. And here we're going to see a little bit more of theory of the physics, which is going to help us to calculate this overpressure. So now we know that we have overpressure in some locations. The next step is actually to quantify that and to calculate it. All right, in order to do that, what we're going to use is what is called the porosity of a shale as a function of effective vertical stress. And this, I hope that this is called a compaction curve, and it makes sense that the higher the effective stress on the rock, the smaller the porosity is going to be, right? What is not straightforward now is to say the deeper the shale, the smaller the porosity is going to be, because this is when we run into cases in which we might have overpressure. If we do have hydrostatic pore pressure, then it is correct to say the deeper the shale, the smaller the porosity, assuming that we are always talking about the same shale. And in this case, you could interchange these axes for depth. And the bigger the depth, the smaller the porosity. However, when we have overpressure, this is not going to be the case. And we're going to have departures from this trend. So instead, when we do have overpressure, what we're going to do is we're going to use the measured porosity from the field. And with that measured porosity for the shale rock, and knowing what is the equation for that compaction curve, these two are constants, fitting constant, the porosity naught and the parameter beta. And knowing that porosity from the field, either from a neutron porosity measurement or density porosity measurement or a sonic porosity measurement, knowing that, we can calculate what is the effective vertical stress at that depth. And if we know the effective vertical stress at that depth, and we know what is the total vertical stress at that depth, something that we have already seen how to calculate, then you can calculate pore pressure. Pore pressure is just going to be, if we move this one to the left-hand side, is going to be total vertical stress minus effective vertical stress. And this is a procedure that we're going to use in order to calculate the actual pore pressure and in order to determine in a place if there is overpressure. So let me go a little bit lower over here. Here, example number 26, it shows step by step the procedure about how to calculate this pore pressure following this compaction curve. Again, first you calculate total vertical stress. Second, you calculate effective vertical stress from the measured porosity. And last, you calculate the pore pressure with the equation of effective vertical stress. And the result is going to be that for this example, we can see this is an actual calculation of overpressure following this procedure. We see that using the porosity of the shale measured with logging tools, we can see the deviation of porosity from the normal compaction trend. And in this case, we can see that the deeper we go, you would expect a lower and lower porosity, but at some point, if we do have overpressure, then there is going to be a deviation from that normal compaction curve. That deviation is going to result in the calculated overpressure that you see over here. In this particular case, the true pore pressure is the one which is calculated from the shale porosity and denoted here as overpressure. And it's following this line over here that I'm following with the mouse. And it is not the hydrostatic pore pressure. This is put just for reference. And something very important to notice in this plot too is that effective stresses, it gets smaller and smaller with depth. We're going to see this is actually something very important because this is very problematic for drilling. Usually the smaller the effective stress of a rock, the weaker it is, and sometimes the harder to drill through it is going to be. One more thing to highlight in this plot is that notice that here the overpressure is caused by an increasing quantity of clay. In the second track, we see the percent of sand, and we see that closer to the surface, we have quite a bit of sand. Sand is quite permeable, lets that fluid escape, or that water in this case, escape nicely and quickly. But as we go deeper and deeper and we have less sand and more clay, then that's a moment in which overpressure starts to kick in. Okay, um, there is one more thing I'd like to say before I forget, and it is related to an example, an everyday example of overpressure and pore pressure dissipation. And it's just to highlight the difference between sand and clay. Imagine that you go to the beach and you step on sand very close to the water. When you step on the sand, very quickly the sand, which was the water which was within the sand over your foot, is going to dissipate very quickly. Try that next time you go to the beach. The pore pressure dissipation in sand is very fast. However, try to play with clay or with mud and try to squeeze mud with your hands. You will see that mud is not going to release that water inside very very easily. Instead, the mud is going to squirt through your fingers. And what that is telling you is that the water inside is not going to leave the pore space because there are huge viscous forces that are retaining that water inside the pore space within clays. And it is the same thing with geological systems. And that's why we have this phenomenon of disequilibrium compaction, and that's why in many sedimentary basins, especially the ones which are constituted by sequences of sand and shale, have a significant overpressure as you go deeper and deeper.